Hi, I'm Dr. Tom Calabrese, and welcome to this edition of Insights into Computer Science. In this segment, I will be discussing some of the real magic of the C programming language, creating your own complex variables using the Typedef command and structures. If you recall from some of our previous discussions, computer memory is vast. Random access memory in most computers exceeds 4 gigabytes. You may also recall that when you declare a variable in C, such as integer x, you are really asking the computer to choose a place in memory where there are enough contiguous bytes, in this case 4, to make that variable and then map it to the name x. That name is important because it can be used to assign or recall values that reside in the space of bytes. The name, as you know, can also be used in conjunction with the address of operator, or the ampersand, to obtain the address of the actual location where the data is stored, ampersand x. Now, when C was created by Kernighan and Ritchie, they chose to use words like char, integer, short, and long as the basic data types that were available in the language. I prefer to think of it this way. Char is a request for 1 byte of memory. Short is a request for 2 bytes of memory. Int is in a 32-bit machine is officially guaranteed to be 2 bytes, but in most implementations you get 4 bytes and even larger in some implementations. A long is 4 bytes. A long or double is 8 bytes, and a long double is 12 bytes. For a particular system, the only way to know for sure is to use the size of function, such as size of int, to get the supported size from any type that's in your machine. You should pause this video and try using the size of function for a bunch of different types. So for example, put it in a print statement such as print, the size of int is %d\n for the new line, size of int. You'll get a 4. Try them all to get a real feel for what the sizes of the different variable types are. So how did it go? Now, for the first new trick. Suppose you don't like those names and want to make some new variable types. Well, in C, you can, using the typedef command. Now, typedef should come at the top of your program, before the int main void line, or the main line of your program. Remember that everything above the main program line is global. That is, the item can be seen and used by all programs and functions you create. That is not a good idea for variables, but for constants, typedefs, library files, etc., it's essential. So suppose that, like me, you find words like char confusing. Well, we can fix that. Just type typedef char space 1 underscore byte. Of course, we end everything with a semicolon. Great. What you just did was create a variable called 1 byte. Now, inside the main program, you can use it. 1 byte x as a declaration. Just created the variable x that is 1 byte long. Don't believe me? Well, check it. Say printf, parentheses, quote, the size of 1 byte is %d, \n, size of 1 byte, then 2 parentheses and the semicolon, and you get a 1. Next, create a variable called 2 byte, typedef short 2 byte, and so on. You can even create sizes that don't officially exist. Typedef char, and then create the array 3 underscore byte, square bracket, 3 square bracket, and semicolon. This creates a 3 byte variable. So check it. Printf, the size of 3 byte is %d \n, size of 3 byte. This is great fun, right? So now this is just the beginning. In our next installment, we're going to work with a more advanced data structure called the linked list and discuss how to make them and what they're good for. Linked lists depend on a special kind of variable called a structure. Structures allow for the grouping of primitive variables to form a more complex variable. Sounds confusing? It's really not. Suppose you're a teacher with a class of students. Each student has a first name, a last name, GPA, year in school, and whatever other information you want. You could just represent all this information in separate variables over memory, but then things would be hard to find. You could try keeping separate arrays of names and GPA, etc., and unifying them by the index number, meaning that you want to be able to say index 1 in all of those arrays are a particular student. But what is more interesting would be to use a structure that would keep all of the data about a student together in a contiguous space. To do this, we use the keyword struct. Struct is a command that tells the compiler to add up all the sizes of the variables in the structure and put them into a contiguous or together space. So, struct student1, curly bracket, and then add all your variable types. Char first name, we'll make it an array of 25. Char last name, array of 25. Integer year, floating point GPA, curly bracket close, student1, would be essentially asking the compiler for 58 bytes of contiguous memory to be used to hold information about student1. Now, to populate this structure, you would use the selection operator or the dot, such as student1.fname equals, let's say, Lyle, and student1.lastname equals Brown. Student1 year, say he's a sophomore, 2, and student1 GPA, 3.9. You can use these in all kinds of ways, like if student1.gpa, meaning the GPA field for student1, is greater than 3.2, then print out that %s, which would give you first name, last name, is an honor student, and then you put the two variables student1.firstname and student1.lastname in your print statement. Then you would get Lyle Brown is an honor student. And you can get the size of this structure with the size of command. So if I said size of student1, it would return 58. This all sounds great, but we can take this even further. At this point, you can see that even with a structure for each student, we are still pretty limited from an organizational point of view. The way we are approaching it, the teacher would need to go into each structure and work on things for each student, one structure at a time. That would be a tough thing to track. But remember our Typedef? Well, it turns out that we can put that to some good use yet once again. Instead of making a student structure for each student, let's create a variable type for a generic student using the Typedef command, such as Typedef struct student underscore t. Now we're going to use the underscore t from now on when we build these kind of structures so that we indicate that it's a type. Remember, a type variable doesn't actually create anything, it's just a map. Now inside there, inside the curly brackets, we're going to use the elements again. Char fname 25, char lname 25, integer year, floating point GPA, and then we would close the structure and again put the tag student underscore t and a semicolon. Place this above the main function header. Notice, I called this again struct student underscore t with the t meaning type for clarity. Now, inside the main program, let's do something really cool. Teachers have classes and classes have students. So, with the use of our new student data type, we can create an array of students called, let's say, class and then the class number 1, 2, 3. Simply by executing the command student underscore t space class 1, 2, 3 and then the square brackets, 50 square bracket, semicolon, and now you have an array of 50 students. You can fill in the GPA of student 2, let's say, by simply executing class 123 sub 1 dot GPA equals 4.0. Remember, we started counting at 0, so student 2 is referenced by the index 1. But now we can use arrays to warehouse our structures in terms of particular classes. So this is really useful. One thing to consider is that you can keep abstracting in this way and make very powerful but still rudimentary data structures. There is so much more you can do. Next time, we'll take this all one step further when we examine self-referencing data structures and linked lists. So until next time,